ask it to light up this little light bulb a little bit, you can see that it draws more current here, and you can hear it slow down. You can hear the tone change. Okay? And as it slows down, it generates less reverse voltage. Do you understand? So here, now the current is moving in it. It's starting to motor. It's starting to motor against itself in the opposite direction. So when the machine is running as a generator, we'll call the back EMF the reverse direction motor torque. When it's running as a motor, we will call the back EMF the reverse direction generated voltage. So what you can see now is that this is exactly the same machine, and you can bias which effect you're looking for. If you actually force current through it, like from our power supply, it motors ahead, and the motoring effect gets ahead of the reverse generation. In this situation where we're mechanically forcing it to turn, the generation effects get ahead of the reverse motoring effects, and therefore it will push electricity out of the system to light external loads. But both effects are happening in both machines simultaneously. So now let's go back to the book and take a look at the symbolic representation of what we just saw on the bench. Here in our diagram, it says the illustration represents the back EMF as a battery opposing the applied voltage, with the total armature resistance shown symbolically as a single resistor. So this is a symbolic representation so that we can understand the functions going on in the circuit. And in fact, this is the exact physical arrangement of our test motor. We have a permanent magnet field on both sides of a current carrying conductor that happens to be in the slots of the armature. We have commutator sections here with brushes going out to our DC voltage supply. And as this thing spins faster and faster and faster in the field, this value of the back EMF, or what they're calling the counter EMF, becomes a larger and larger value, which opposes the input voltage. And so what we see is that the resistance of the armature winding, which may represent in our motor maybe 20 feet of magnet wire between the commutator sections, that represents a very, very small resistance. And so this represents both the resistance of the armature coil wire and the brushes. So these are carbon brushes against a copper commutator, and typically there's somewhere close to about a 1 volt drop here of just voltage that can't be recovered. But so you can see typically that there's quite often something on the order of 1 volt to half a volt or something like that, which can never be overcome at the bottom of the situation or under idle circumstances. And that's pretty much this, because the actual resistance of the windings is probably on the order of somewhere between a tenth and a hundredth of an ohm. So what's really holding the current back in these situations is the back EMF. And this is also noticeable, and we didn't demonstrate it before, but I'm sure you've seen that when this type of motor starts out, you give it 12 volts at the beginning, it leaps to very high speed as quickly as it can, because when there's no back EMF, in other words, when this is not spinning and generating a reverse voltage, it draws its maximum current at 0 RPM, and the motor is extremely strong when you drop the full voltage and the full current across the armature windings. And then as it speeds up, the current starts backing off because this value is rising, and so the motor regulates up to a top speed. Now let's take a look at what the book says about this situation. So here is a blow-up of the paragraph that is directly underneath this diagram that I just showed you. And here's what it says. What actually moves the armature current through the armature coils is the difference between the voltage applied to the motor minus the counter EMF. Thus, the applied voltage minus the back EMF is the actual voltage effective in the armature, and it is this effective voltage which determines the value of the armature current. Since generally I equals E divided by R from Ohm's law, in the case of the DC motor, the applied current is equal to the applied voltage minus the back EMF over the armature resistance. Also, since according to Kirchhoff's second law, the sum of the voltage drops around any closed circuit must equal the sum of the applied voltages. Now, I must admit that I agree with absolutely everything this says. So this is how this motor works. Now, let's take a look at another analogy. So here is our simple back EMF analogy, and this is set up very similarly to what we saw from the book Basic Electricity. What we see is we have an applied voltage, and in this case we're just going to say these two 6-volt batteries give us a 12-volt supply. So that's our applied voltage. And what we're going to do to simulate our back EMF is we're just going to take another 6-volt battery here and put it in opposition to the first battery so that they have a negative common ground. And so what we see is that this point in the circuit is plus 6 volts potential, and this position is plus 12 volts potential. And then we have our little load device. In this case, it's a resistor with a little bit of light coming out of it, so we're going to call this a little 6-volt light bulb. And then here we have an amp meter with a 0 to 6 amp scale, and it's just on the first notch here, so we're going to say that there's 1 ampere moving in this circle. So by what we just read in the book, the applied voltage minus the back EMF gives us our effective voltage, so we can see very obviously that there's 6 volts running this, and since there's 1 amp here by Ohm's law, we can calculate that the resistance here is 1/6 of an ohm. So what we see is that this thing here, our little load, is doing a number of things. First of all, the voltage here is the difference between the applied voltage and the back EMF. And the resistance here in relationship to this effective voltage here is what determines the amount of current running in the system. So the resistance here is the regulator in the system. So we can clearly see, now that we have all the values, we see 1 ampere, we see 1/6 of an ohm, we see 6 volts on the load, we see 6 volts back EMF, we can clearly see that there are 12 watts moving through the system, 12 volts times 1 ampere, and 6 watts of energy are dissipated here at our load, and 6 watts are represented here. Now, if this is a real battery, what's happening is that this 6 watts here is actually charging this battery. It's in opposition to the discharging battery, so obviously this 6 watts represents 6 watts of charging potential for energy being stored at a rate of 1 ampere. So this regulates the charge rate of our battery here. So let's now go back to our motor analogy and see how all of these things fit in. Okay, so here is our back EMF analogy again, and I've used almost the exact same drawing, except now I've plugged in the values that we saw from our back EMF demonstration in the motors, where we clearly saw that our applied voltage was 4 4 volts right on the power supply meter, and our current running in the system was 3 amps, again on the power supply meter. And here the back EMF we saw on the yellow meter, which was the voltage being generated by the second little motor. It was turning at the same speed as our primary driving motor. So we have all of these quantities by measurement. We have this on the meter, this on the meter, and this on the meter. So we can solve for the other two things, and so we can clearly see by the book that our applied voltage minus our back EMF creates our effective voltage. So we can clearly see that 0.8 volts was the effective voltage on the armature. And now, since we have 0.8 volts and the current, we can solve for this quantity. So again, using Ohm's law, we can see that the resistance is going to be equal to the voltage divided by the current. So 0.8 divided by 3 gives us a resistance here of 0.26 ohms. Now, this is where the books stop. And there are two fundamental corollaries here which are never mentioned in the book. So this is the first big secret about back EMF. And that is that you saw in our light bulb analogy that I just showed that we can figure out how much energy is dissipated here at this section simply by multiplying this times our current. And so what that means is that the energy dissipated in our armature winding is 0.8 volts times 3 amps, or 2.4 watts. Secondly, we can look back here at the back EMF, and we see that it is 3.2 volts. But in this case, this is just a voltage on the winding, and there's no storage mechanism involved with it. So there's no way to store this energy in opposition to our applied voltage. So what this does, what the back EMF does here, is it simply destroys 3.2 volts. And the fact is that only 0.8 volts gets through the system. So here's what we see. We see that 3.2 volts times the 3 amps, or 9.6 watts of energy, is destroyed by the back EMF, and 2.4 watts of electricity is what creates all of the mechanical energy that the motor puts out. That is the secret of this problem, that the back EMF in this case is destroying 80% of the energy that we are applying. Our 4 volts times 3 amps is 12 watts. 9.6 watts is destroyed, and 2.4 watts is what creates all of the mechanical energy the motor puts out. So, with this in mind, let's go back to our dynamometer test and see what this implication means about the efficiency of the motor. So here are some revised figures for our dynamometer test, and as you can see here on the second line, motor under load, these are the values that we saw. It was 12.1 volts, drawing 7 amps, and it had slowed the motor down to 1864 RPM. Now I went back and actually looked at what the motor was doing when it was idling, and it was drawing same 12.1 volts, but it was only drawing 1.1 amperes, and it was turning at 2235 RPM. So in order to understand what kind of back EMF this motor might have been generating at our test speed here, I went back and actually just powered up the motor in an unloaded condition and just put in enough voltage to turn it at that speed, and what it drew was 10 volts. Now we've seen in this motor, because of the voltage drop on the carbon brushes and what little resistance there is left on the armature windings, that typically the back EMF has been running approximately a volt below the applied voltage in unloaded conditions, and it was even slightly higher than this in the smaller motors running at lower voltages. But I think it's fairly safe to say, since I didn't have the complete setup to run both motors and like motors of that type, but I think it's reasonable to believe that at this speed, the back EMF generated by this motor is approximately 9 volts. So the effective voltage running our motor under our load test was, by the book, the applied voltage minus the back EMF equals the effective voltage, or 3.1 volts was what was driving our motor forward under our load test. And so this gives us also the beginning of an understanding of the possibility of developing a coefficient of performance for these motors based on the function of the back EMF. So if we look at our effective voltage, which is what motors the motor forward, and divide that by our applied voltage, which is what we actually have to spend to get it, we can get a sense of what a COP is, or a coefficient of performance of the motor, based on the back EMF function. And what we see is that the COP of the motor under this circumstance is 0.256. So we have to ask this question: what is the real power driving our motor during our load test? Because this gets back to what the efficiency really is. So if we look at the fact that what drove our motor forward was the difference between the applied voltage and the back EMF, so that's our effective voltage, times our current that was drawn at the time. So there's reason to believe that what drove our motor forward under our load test was 21.7 watts. Of course, we had to put in 84.7 watts to get it, but this is what drove the motor forward. Now, if we look at converting that again to horsepower, 21.7 watts divided by 746. So our real input was 0.029 horsepower. If we plug that into our efficiency equation, what we come up with is that the motor is actually 300% efficient at providing mechanical energy production from effective input. So, and this is by the book. So, if we look at the real efficiency, which is 300%, and we multiply that back by the effect of our back EMF, which is the 0.256 COP, then we come right back to the original number that we calculated during the first calculation of our dynamometer test, which is 76.7% efficiency. So there is at least reason to believe, not only in the numbers but on the bench, that we must draw this conclusion that the back EMF in the system masks the excellent performance of the motor and is actually in the process of hiding it behind a very low COP. Now this also leads to a clear understanding of exactly why most dynamometer tests for induction motors of this type, it is recommended that you slow the motor down to 1/2 of its idle speed to take the measurement. And now we can see why this is such a good idea, because it raises the COP to about twice what we saw here. In other words, if the back EMF is dropped by 50%, then we can get a lot more effective power creating mechanical energy. And with the COP up to 0.5, then these numbers can quite often get up into the upper 80s and maybe even low 90s for a little motor like this. It's not uncommon. So here we have a very interesting situation which tells us something very important about the back EMF and what its function is in the motor. Okay, now before we get all goofy and think that off-the-shelf electric motors are producing 300% efficiency, let's get away from our analogies and our symbologies and our representations and get back to the back EMF reality. And the reality is, and I've got this drawing here set up to have the values that we just saw in the dynamometer test again. So we have an applied voltage here of 12.1 volts. Our amp meter now is reading 7 amps. And here's our little brush commutator sections. And here is our inductor. And we can see that both the forward and the backward EMFs are distributed evenly throughout the inductor. So these aren't a series event as we saw in the analogy drawings. So in the analogy drawings it was obvious that these were separate events. But here they are concurrent events in the machine. And so they can't be separated because they're actually happening on the same component. In other words, when current moves through this winding in the magnetic field, it produces a mechanical action which motors the motor forward. When that happens, it actually starts moving these coils through the magnetic field, and that generating action generates our back voltage. So what we see is that both the motoring and the generating effects look like mirror images of each other. And they're quite often taught to be mirror images of each other. But actually they aren't. They aren't mirror images of each other. And this is very important to see. In fact, they are actually reciprocals of each other. And we saw this on the bench. We saw that when the back EMF was the highest, the motoring effect was the weakest. It might have been the fastest, but it was also the weakest. So the mechanical energy production was the weakest when the back generated voltage was the highest. As we started slowing the motor down, the back EMF dropped and the motor torque rose into the load. So the mechanical energy production was getting stronger as the back EMF was getting smaller. So you can see that they aren't mirror images of each other, they are reciprocals of each other. And this tells us that they are not the same thing. They are happening in the same component, in the same location in the motor, at the same time. And that is why they cannot be separated from each other in this configuration of motor. The only thing keeping them from being separated in this situation is the geometry of the motor. So, there's two things that I want to bring to your attention. The first is, and this is an ordinary electric motor, when we put electricity in, this applied mechanical or electrical voltage and electric current do two things. And that is, they produce a mechanical energy manifestation out as torque on the shaft, and It generates electricity. It does two things. It produces mechanical energy output and it produces an electrical energy manifestation. In this case, the electricity is applied against our input and subtracts from it. Now, the question is it possible to create an electric motor that takes advantage of all of these things? In other words, we put electricity in, we're going to get mechanical energy out, and we're going to get electricity produced. And is it possible to create a geometry of machine that will allow this electricity to come out as a positive quantity and not act against our applied voltage? And the answer is yes, this is possible. But we can't do it with this geometry of machine. We have to look for something else. Now this is a repulsion motor. In other words, when current is applied to this coil, it creates a pushing action against the magnetic field. And it's very strong right in the middle of the field, and it pushes its way out of the field. And what we're going to look at is the opposite situation. We're going to look at an attraction process, because it's in the opposite process, not a repulsion motor, but we're going to look at an attraction motor and see if this won't allow us to separate these effects and create a much more interesting result. This is the cover of the 1940 edition of The Boy Electrician by Alfred P. Morgan. And this book was a hands-on book for young boys who were learning about the new science of electricity. It is filled with